graphene in tie binding. I remember to bring a paper from some 15 years ago or something, tie binding, and you can see that they do calculation, they do more than the first neighbors. But it's impressively close to the ab initio results. I'll let you have it. This is the tie binding, the black one, and the dashed one, and the full line is ab initio, which is supposed to be exact. So it is very close. And they also compare tie binding, taking into account also third neighbors, which is many more. And yes, it is approaching, it's closer matching with the ab initio. So it is a powerful technique. Before we continue with the applications of the band theory, I would just say 2-3 words about the approximations you made so far for the calculation of the band structure. So you've done nearly 3. Electron model. Okay, and tie binding. This one is fresher, I suppose. There were some assumptions that you've done while discussing it. So you talked about the extent, the spatial extent of the wave functions. Maybe I can give example of the sodium. Here, sodium, I think it has 11 electrons. It should be, okay, let's see. 1s2, 2s2, 2p6, 8, 10, yeah, good. 1s electrons. What happens? How are these densities, wave functions? Okay, I shouldn't show it like this. So, 1s, no nodes, and very, very close to the, actually the sign here is completely relevant. It's very close to the 0. And this is the distance of the nearest neighbors. I think it's 3.7, I believe. But okay, I might be wrong here. So this is the next atom here. So first atom, second atom in the BCC lattice of sodium. So it will also have the same behavior here now. And the 2s will have one node. Something of that type extends a bit further. It's not easy to draw it. 2p has no nodes, but is extending more. Something of that type. And then the 3s, it will have 2 nodes. It will do something like this. And then here, it doesn't have time to decay, because it will, from this side, it will overlap with the wave function from the other side. So you have a significant overlap in between the 2 atoms, which means a very strong overlap. And here, this would cause a very large T if you apply tie binding on this. This says you cannot, by no means, apply tie binding for this situation. And indeed, sodium is a typical 3-electron system. It is alkali, that 1s. So if in the outer shell is 1s or 1p, you cannot imagine to apply tie binding, because the overlaps will be strong. So one of the conditions for the application of tie binding is that the overlap of the wave functions from the neighboring sites is very small, close to 0. that of course you can define the atomic functions that you have, and that the atomic potential itself, is actually not extending too far. This I will come to in a second. But these two approximations have something in common. They are both independent electrons. I'm not sure now they have time to discuss that. They completely disregard the interaction between or among electrons. Completely. It's too complicated, way too complicated. And they both can be viewed as a perturbation theory, as coming from the perturbation theory. So what is the basis for nearly free plane waves that you know? And how is the energy dispersion? Of the plane waves. Something of this type. In the tie binding, it's as opposite as it can be. No? One limit is something plane wave. They are extending all over. No? Here, atomic functions, which are localized at an atom, at one side. Atomic functions. And their dispersion is what?
Cosines.
No, just atomic functions, not tie binding.
Atomic wave functions is the basis.
Yeah, but in energy dispersion. You know it, I know you know it. Constant lines.
Yeah.
It just, so it is as far, well, I can go from the negative so you don't get confused. It's okay, I could have put it a bit lower. They essentially do not disperse. They are so localized. At just one energy they exist. They have exact energy at which they exist. And what was I going to say? And then what happens when you actually, this is the basis, no? This is the starting point. But then you add the potential. Here, the potential is the weak potential of the lattice. The weak cosine or whatever. So it can be taken as the perturbation potential. So the condition is that the potential, that the weak periodic potential is very small. No? Small. What is the condition here to apply? In the tie binding, I'm saying it can be taken as viewed in the perturbation theory. So I have my atomic system, just atoms put there, and what is the perturbation there? The analog of the weak periodic potential.
The perturbation from the potential of other atoms is the perturbation.
Yeah. Okay. So here the condition is that the difference of the whole potential minus the atomic side potential should be very small. So you have this you've seen 1,000 times by now, I think. This is the whole potential. I mean, it's always drawn in 1D because it's the only possible thing to draw, but it's in 3D. No, you always have from all the atoms. And actually the difference of this and the atomic one. So this is extending up to some point. So potential whole minus the atomic one, minus D minus R should be much smaller than this potential. which means it says that this here, what is left out after you remove the atomic potential at that site, should be small. That the potential of a single atom should not be extending very far, in other words. So this is the condition. So I already mentioned the nearly free can be applied to systems with 1s, 1p valence electron. Alkalis are the best example. Here, when can this be applied? In which cases? I mean, here it's obvious it cannot be in 1s valence or something. It's terrible. But when can it be?
When the width of wave function is way smaller than the distance between atoms.
Yes.
That is constant.
Okay. In general, it is, I do a drawing, in the electron systems. They're also metals, like these guys there. They're metals, but the d orbitals have much smaller dispersion than S and P. I think this we already discussed for the pseudopotential method, for the expansion to free in the plane waves. The d electrons tend to stay in the band structure quite flat. They would vary a bit from the flat line. While S and P, they always have this parabolic basis. So, for D in the valence, I think it is from the fourth to 8th column, I'm not sure in the table. And for the insulators, of course, when you have no states at the Fermi energy, then you're sure. So this is the differences and similarities. So what happens after the approximation has been done, depending on the band structure, on the brilliant zone, in the free electron, nearly free, you will get gap openings, no? You remember that. Okay, it should be a bit more. No, something of this type. So it opens. So you open gaps, depending on the strength of the potential. What happens here? Today it's a bit wet. An improvement. I could have drawn a bit bigger, but okay. So. The same thing, it will be energy levels. Opa. And then what happens when you change the distance? So this is atomic case. You have one atom here. And then you bring a second atom of the same species closer. So I'm drawing here 1/r distance between the atoms. What happens? They start overlapping at some point. And this single line actually gets some width. Slowly, 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 it's getting certain width. And each of them. And that creates bands. So the closer they come, the stronger is the overlap, and the wider is the band. That's okay? However, the condition for application of the tie binding is that the width of these bands does not become larger than the difference between energy levels. It's like the rough application, I mean, when you can judge if to apply tie binding or not. Did I say everything here? Any questions on this? This was just a short review to finish with this, because now you actually go apply what we learned here in general, assuming that you know band structure at the bands. These are just the two simplest methods. In reality, what you will use to find the band structure is something more sophisticated, some ab initio methods or density functional theory, something of that type. Questions?
The thing that you mentioned, that the case when the tight binding is can be applied in the way that the width of splitting has to be smaller than the difference between energies.
This is very rough. I think this is a school. It's not always true.
In this case, for example, on the drawing,
Yeah,
when the second and third one, then this doesn't.
Yeah.
Okay.
So, but it's a rough thing. I mean, when you're sure that it can be applied. Yes.
Which of these methods is DFT more related to?
Okay, you answer this to me. Okay, imagine that you have a pseudopotential method, and then you describe the ions, the cores with a pseudopotential. So you don't have the real thing here. You actually just have a very strong potential, but a finite. So we don't know what's going on inside, but you replace with something strong, a whole core. And all the valence electrons are expanded in plane waves. So? Yeah, I mean, the basis-wise, it's closer. But however, the density functional theory, in any kind of implementation, you don't have to use plane waves. You can use Gaussians, for example. You can do anything to any basis. It can actually, just with many more functions, can describe any d states. But in its original version, with very few plane waves available, because there was no computers to do something advanced, you could do very well simple metals. Very simple metals. That was the kind of first things to be done. Now it's because we can use 100-fold big bases. Okay, any questions? Good. Today we'll start on the applications of the band theory. And on transport. Everything I'm going to do is kind of semi-classical. So it is just to get some concepts. It's not really the best there is today. No? Transfer properties. I will actually use what we know about the electronic states in a crystal, in a Brillouin zone, to derive some properties, and starting with the transport properties. So it's obvious that it's very important to understand how the conduction occurs. You put a field and what happens within the material. The earliest theories, consistent theories, were at the beginning of the 20th century, 1900. This you don't have to write, I mean, this was just a few years after the discovery of electron by Thomson. And it was Drude who made up a simple theory. Until then, existed a kinetic theory of gases, and in which the gases, the molecules, were imagined as solid spheres, which were moving on straight lines, and then colliding, and just bouncing, using Newtonian mechanics. So he kind of used that to start up a new theory, based on something so simple. But he understood that the system is neutral. So he had electrons, which he just learned, I mean, their properties, they are negatively charged. And he postulated, didn't know exactly, that there also should be some heavy centers positively charged. But he made up, I mean, it was really impressive how strong intuition he had. So he imagined something like a strong center, big, much bigger, much heavier than electrons, in which there were some bound electrons around, and then everywhere around were the remaining electrons. And these were still spheres, and they were acting as places, and they're immobile. He imagined these positively charged constructs to be immobile, and they were just there to scatter electrons. Something very, very simple. He was working in the independent electron approximation, and also free electron. He was completely disregarding. So you tell me, what does it mean, free electron approximation?
There is no potential.
He was completely disregarding the effect of these positively charged. So they were just there to scatter the thing. There was no interaction. And he managed, based on really intuitive arguments, to find the expression formula for the current in the electric field. So the current density, this is a vector quantity, is obviously proportional to the electric field. I apologize, I'm very used to write electric field this way and the energy in this way. I think the Nadia was using that, she was using the opposite, I'm afraid. So please bear with me. I'm so used to it. If I start changing, I will do it one lecture but not the next one. So for me this is electric field. With some proportionality constant, sigma. And he was able to express this sigma, as dependent on the density of electrons, on the scattering time. So they are going around, they scatter, and between two scatterings there is some average time. This is the scattering time, inversely proportional to the mass and the charge. And I can tell you that actually this expression from the conductivity is something quite reasonable based on the most basic simple arguments. So today we will start discussing what creates current, what you have to create a current in a system, and how does the band structure enter? Why do we care? If you want to see conductivity, transport properties, how does the band structure enter? So for that, let's see first how I can express. Okay, the current can be expressed as, well, depends if I want current density. If I put a density, then this is the current density. Okay, it can be expressed as a density or as the absolute quantity, the charge and the velocity of electrons. No? You okay with that? And this velocity should be actually sum over all the, for each case, so it should be actually a sum of all the particles all the occupied levels. So, okay, and now we have different meaning of n. I was going to write n as the level, but then the density is not good. So let's not talk about charge density or current density, but of the current absolute. So the n means the level. Okay, and I'm summing up over all the occupied levels. Is it okay? I made a bit of confusion with n. So n is the band number. And I will add up all the levels. Fine. So I want to express the velocity. How do I express it? To come to the current, I have to know the velocity. So this can be taken as the expectation value. It depends on R of the momentum operator, no? This you know. And this is equal minus RH of M but I can also write this as a block state, separating the phase and the periodic function. I stopped writing the over. It's lots of writing. So now I can take this gradient, first of the phase part and then of the function. So this will give IK. Plus of this. So I have these two inside. They give 1, so I can just okay. So here, what I'm getting, again, these two can be multiplied. Take them out. I'm getting expectation value of IK, which is a constant. I can just take it as IK. And then I multiply I and I, get minus I times I is 1. I'm getting K, H, over M, plus, this is P over M. I think it's correct, but let me check. I don't forget some factor. Yeah, good. Okay, we got something a bit complicated as an expression for velocity. We have two terms. Yeah, finish copying so I can analyze. Now imagine you had a free electron system. I forgot to say that actually Sommerfeld came 30 years after Drude and improved the theory, especially for the specific heat problem, which was present before, and he just added the Fermi-Dirac distribution in this model, and it greatly improved. The specific heat was actually corresponding to experiments. And so in Sommerfeld, which is a electron picture, Sommerfeld, what will be the velocity? If you have 3 electrons, then UK is a constant. Now you just have E on the IKR. And this term is 0. And you have just this. So you have a free electron kind of velocity plus something else. This is non-free electron contribution, correction to the free electron. But what is this? I mean, how do I get this? Now you have to trust me that it will be useful if we evaluate the gradient of energy in K. It will become clear after we get it. So I want to find the gradient of energy, also of the band. And but before that, how do I energy is the expectation value Hamiltonian. But I can also consider the psi as the block function and separate it into UK part. Actually, right away, you've already done the Hamiltonian in K. No? So you know I don't have to derive it, that it can be written this way. Other question is if I remember this form, but you know this. You derived it in the class. Yeah, Amal, when you show like this, it's very confusing to us. I had an Indian friend who kept doing this and I kept repeating 10 times. Okay, let me... Okay, let me just write. Does it have a factor before? Not. I always have to check this. Yeah. It's plus. No? Correct? And I will find the expectation value with these periodic functions. And I'll take the gradient. So this is what I want to do now, if I find space for that. It takes some writing up. I want to keep this because it will compare to this part. Okay, let me start writing here and then I don't have to delete this. So, we will write the gradient on this. This is what I want to evaluate. So, I can apply the gradient to this part here. first part is I'll apply the gradient here. But then this Hamiltonian acting on this UK gives me E of K. So I can write it here. Okay. Then I can apply the gradient to this part. I again have EK out. And now it is the central part. The gradient of this HK. Like this. So this doesn't depend on this. Here, on K, here I will just get 2I gradient minus 2K. Okay. Everyone is following. It's nothing smart really, just a bit of writing. Let's analyze this first part. This I can write. The first part is as E of K m times the gradient of the norm. But this is a constant. So this is 0. So these two guys are gone together. And I'm left with this part. Minus h squared over 2m. No, actually, let me not write it out. But let me put plus. A bit more space that I can write the constant. So, if I add one h here and m, I'm getting p operator. Okay, so I'll write minus I h gradient over m, and 2 and 2 cancel, and I'm getting left out minus h
Key.
No, plus. I was looking, shouldn't it minus? It's
Yeah,
plus.
no.
Plus h. Good. Plus h. And the second term is 2 and 2 cancel. H k divided by m.
Plus.
Plus. Right, plus. Okay. So this is 0. I don't want to get that. It's not contributing. That the gradient of energy is equal to this. And this is something very similar to this. It's equal to h times hk power n plus this a bit weird matrix element. Is everything correct? Yes. So this is just the same thing. So I'm writing that the gradient of energy in K is equal h times the velocity. other words, I can express the velocity as the 1 over h part of the derivation, is it okay? It's really basic. Although it sounds like a very simple result. No, you just have one derivative to take, that's it. If you think of it, it's something. I'll wait a bit so that I can cancel some stuff from the blackboard. Okay, then let me cancel this part. So what is the meaning of it?
It is like a slope in a E versus K graph.
It says that actually it strongly depends on where in the brilliant zone you are, because the slope is not constant. And that's highly non-trivial.
And it's periodic.
And it's periodic, of course. But that kind of you could assume, no? By going from one to another brilliant zone, it has to be repeated. But this depends on the you have energy versus K. Let's draw some tie binding band in 1D. Many things are done here in 1D actually, for the simplicity, but they of course apply to 3D, same conclusions. This is the band dispersion, this cosine Kx, no? What you've seen, and then the velocity. Actually, in 1D, I don't have to write vectors. So I have here 0 and 0 and 0. These are the boundaries. 0, 0, and 0. Here, the band is going down, is reducing with k, so it has to be negative, the velocity. Here it's positive. So positive and negative. It becomes asymmetric with respect to the gamma point. And here is the point of inflection, which will give the maximum in both cases. So I'll have a maximum here and a maximum here. This is the velocity. I think tomorrow I will analyze a bit how it changes to the brilliant zone. Give you time to actually review this lecture before that you have questions. So it won't be constant. And imagine a complicated 3D band structure. You will have all kinds of behavior. So what is the current in equilibrium? We just derived the V, and we can express the current. I will hope it's okay to write it like that. the minus sign. Good. So in equilibrium, I will have a number of states occupying the bottom of the band, let's say, symmetrically around the gamma point, up to here, whatever. For example, what can we tell right away about the current? From the velocity. Whatever amount I occupy,
It seems like it's zero.
I will have equal amount of positive
And
and negative velocity.
so zero.
So it sums to zero.
Yeah.
The current is zero. Equilibrium. So, equilibrium. It means that actually the system is undisturbed in its ground state. There is no external perturbation. There is in its ground state. So the levels are occupied by the energy. But this is not so surprising. We know that if you have a copper crystal, there is no current if it's in equilibrium, no? So we just confirm what we knew, and we can actually derive it from the. Sorry, I forgot to say. This is called Bloch velocity. Not surprisingly, I suppose. And actually, to derive this Bloch velocity, we didn't use any approximations, if you think of it. It's really a solid result, very general and solid result, not based on some heavy approximations, nothing. We use just that to express speed and the Bloch theorem. Operators, quantum mechanical operators. So, we find that at the equilibrium there is no current. Obviously, we have to make it out of equilibrium by
Applying the electric.
yes. So we need a field. And we know from experience that you get the current. When you have a conductor, you put the electric field and you get the current. So now let's consider, now this goes, what happens under the influence of electric field. So I consider something like that. Again, a band, and then apply. This is energy versus K, and I apply electric field. If the field is there, the force is acting in this direction to the electrons. It's minus E, minus electron charge times the field. And what happens? You will get the states. These are all the states with K. You get a force acting on them, pushing them, better word, pushing them to move. And this electric field will actually cause transitions. From K1 to K1 plus delta K. And to express that, we would need to use the Fermi golden rule, which I'm not sure you've covered in quantum mechanics. No, you just studied quantum mechanics. So, but it will come, I think, this year, in which you will show that the transition, I forgot how I called it, transition T from the state I to state F depends on the initial state and the density of states. Okay, right now. perturbation potential, or H prime. You can call it H prime. It's comes to the same. I mean, to derive this thing, you have to assume that you are doing a very small application, that the jumps are much faster. And actually, sorry, I didn't mention that the field has the time dependence. Now, electric field has a time dependence. E0 times. And the full form is this now. But okay, the time dependence, so that the jump from state to the neighboring state occurs much faster than the time dependence of the field. However, I'm not going to derive this, but it can be calculated. And we can actually observe how K changes. What is the rate of change of K? So for that, let me find the energy, the rate of energy change, which I can write as the gradient times dk over dt. I'm sorry, I'm jumping a bit from 1D to general case. For all the plots and these simple things, it's 1D. But then I'm trying to write it a bit more general, so bear with me there. But maybe you remember from some physics, basic physics course, to what, how you can express the time, the change in time, the energy change in time. You remember? It was something with the force and velocity. There is no factors, I think. So I will express this as h times the velocity times no, actually, let me just change the order. dk over dt times h times velocity. If you remember from some basic physics course, I'm sorry it keeps going. This, in principle, this is equal
Force times velocity.
Yes. So this equals to that. And there is a proof in Ashcroft, in the appendix, I think, for what I'm going to do now. This is semi-classical. This is a very rough, intuitive approach. But it's very tempting to say, I have velocity times velocity, this must be the force. But it doesn't have to be so. If you think carefully, if you have A times B equals C times D, even B can be the same one, does not mean that A equals C. A can be C plus a vector perpendicular to C. So it doesn't have to be, but it can be proven, and that's in the book, that actually this is this. So that the force is equal to the h times dk over dt. And the force is equal to electric field times the charge. Good. So I'm going back to my question, the rate of change of K. Is and the change of K can be expressed as E plus some constant. This means that as you apply the electric field, you will be sweeping to the brilliant zone. In 1D it's more intuitive, along one direction in 3D, and with equal time taking between the two jumps. So this won't depend on the shape of the bands. You're just pushing with a constant rate the states to the brilliant zone. And then how long does it take to go to the whole zone? We can evaluate it. If the lattice constant is A and we are in 1D, so you have 2 pi over A, then there is no need for this. This is tau over H. This is a time to finish one rotation, and the tau is equal. Actually, there is no need for the sign now. It's all just for the time. 2 pi over A, H over E. Yeah, this is the amplitude of the field. This is the time it takes for an electron to make one circle. So you push, push, push with the field, and the electron is going in circles. So it has a special name. It's called the Bloch oscillation. The fact that the electron goes to the brilliant zone and circles. And this actually has been predicted long time ago, soon after the Bloch theorem, but they had trouble observing it. Tomorrow I will mention that. And this is a good moment to give you a very short homework, which takes like 2 minutes, but I think it's useful, so I keep giving it from year to year, is to prove that the x of t oscillates. So to actually get the expression for this Bloch oscillation in a 1D time binding band. A single band. I mean, it really takes 2 minutes. It's a derivative, so like it's not difficult to do, but it proves. Then you see it comes from the okay, now we have the field. Now we can express our current. Okay. So let's find the average velocity. I again want to find the current as the sum of the velocities of all the states. Let's find the average velocity. I will want to write it in 1D, so there is no need for the vector. I can do it as 1 over tau of the Vk T and T, of course. Or I can do it over the period, over the space. And this will be 0 to pi over A. And V of k, yeah, right. V of k, I'll write it here, dk. So let's write it this way. This is equal to the gradient of energy. Okay. And then integral of a gradient is equal to function, no? So I will get the energy at the upper limit minus the energy at the bottom limit. But the brilliant zone in 1D, there is 2 pi over A width. So I'm taking the energy at the points which are 2 pi over A apart. And knowing the periodic nature of the electron bands, the energy, I know that these two values have to be the same. Even if it wasn't 2 pi over A in 0, any two values shifted by 2 pi over A. You agree? So it's 0. My average velocity again is 0. I'm not anymore in the equilibrium. I put the field. This sounds like an impossible situation. Because we know when you put a field, a crystal, a copper crystal in the field, you get some current. Depending on the field. The stronger the field, the more current. So, and we have the field here. And we have these electrons going around. They are just sweeping the brilliant zone with the same period, with the same rate. And the average behavior of that is 0. So not in any moment. In some moment you will get all the states to be here, for example. Now you understand. Tomorrow I'll go a bit more to that. This is just the first bit like introductory lecture. Any ideas?
If we are the reason we are getting 0 is because we are averaging in one single period.
But that's what matters. One period matters.
Because if we take one point, if we have only one occupied electron, and we turn on the electric field, at some time it will be on the positive side of case.
Exactly, in one period, it will be equal amount of time on the positive side and the negative side. So it averages to 0 in one period. You want to take in periods, no? It makes sense. We are here taking situation 2 ideal. There is a huge difference between what we assume here and the real crystals.
It will be the same result even if, for example, we derive that K is also varying in time.
Yeah,
right? So we can transform
that's what
agent
you
of
will
K.
do. That's what you will do for the homework I raised.
Okay.
That you will understand, you will see.
Because we can transform this whole integral of gradient KEK into some integral of time.
But it comes the same. I just chose in K because it's a bit easier to evaluate. You could do it also this way, going through time. You'll get the same.
Okay.
It's just a line more to calculate.
So
So whenever you average or a period, you get in a moment you have a current. But if you average over a period, it comes to 0.
we didn't include the scattering.
Yes, yes, the real life. Physics is beautiful because we can consider very simple situations, but sometimes they're very far from truth. And the scattering will change something in the way the electrons go through the Brilliant Zone. And then we will be able to get a non-zero average. But that I would leave for tomorrow, and now I would solve one problem. If you try to solve it. I would suggest, I think it's important that we keep, every time we try to solve something, so that you feel prepared for the exam. Any questions on the transport so far? No? All clear? Good. I think the most useful is the problem of the square lattice and the tie binding. You solved it? Okay, good. Good. That I would like to analyze. And now you can solve also the number 2 problem, because it had more velocity. In that same sheet of problem. I think I'll build up my muscles. Tracing this. So the question of what you are asked to do for a square system, so you know the Brilliant Zone. Gamma, X and W. You are asked to actually draw iso energy lines, the constant energy lines, for a tie binding dispersion. How far did you get? Did you manage to draw completely? That's not an easy problem. I mean, it's easy to some parts, but overall, not an easy problem. How far did you get? You solved? Okay, good. Let's see somebody else.
I solved everything except A.
A. But you did something. You managed to expand around. Okay. You solved it?
Yeah, but I'm not sure the thinking, the reasoning is.
There are 2 ways to do it. You can do it mathematically, completely, or a bit more considering the physics. Either way is good. Ezra, you have it?
No.
Hello. I know it from yesterday, short time, so.
Should I tell you what I think?
I don't like everybody waiting. I mean, then they
Yeah.
won't get coffee.
Yeah.
We have lecture at 11?
Yeah.
Yeah, okay, so I don't want to keep you too long. But you will see also on the blackboard. You have it solved? You try? You have no time to try. I see. Jesus, you try something.
I read a little bit of the solution.
Yeah, I don't advise this thing. I
It
really...
was like accidental.
Okay. Okay, I don't think it's useful. I mean, I don't care really. I'm not grading the homework, so if you tell me yes or no, I mean, I appreciate if you try, of course, but it's not that you get a grade. It's good that you try and Putri, you managed? Can you come today? Yesterday you escaped the blackboard. Mariana, you managed to solve?
I haven't tried.
Okay, I know it's just one day.
Yeah.
Okay. Okay. Putri, then please come. Let's see. But although it might appear mathematical at points, this problem, it gives you some intuition. It helps you think. I don't like the last problem. The feeling, if it's a metal or it doesn't make much sense. I copied this from a collection of problems from Stony Brook, where I got PhD, from my ex-professors, and I don't think it's this last part is the ideal question, having just one band.
For example, KY equals 0.
Yeah, it's the first one, to expand around the gamma point.
The constant line.
The constant lines is this, it's the analog of the Fermi surface, but just for any energy. Fermi surface is at the Fermi energy. You know what it is in the electron system. Here it says for any energy. What's the shape of the lines? You understand? Okay, so far you've done it only the Fermi surface in the electron system. And when you draw the or a free electron system, you draw this. This is a Fermi surface in 2D, Kx, Ky. But this is also an iso energy line. On this line, it says the same energy for these K points in the Williams zone. In this case, you have to draw this type of lines, but not only for the Fermi energy, for all the, for a couple of energies below the Fermi energy. You understand? And the shape is not trivial. I mean, completely non-trivial, because they have tie binding. Here you knew from the electron, it's a simple case. Here you have to define, you have to reason, you have to arrive to the shape. So this is the problem. So the easy part is around the 0. Can you write? Don't escape. So you're moving. Can you write the dispersion relation? I don't have the coefficients here. And so for very small k, we can expand around the k0. So what is the expansion of cosine k as k goes to 0, cosine x as x goes to 0? It's
1 minus.
yes, x squared, yeah. Both of them. It's y. So actually they both are entering with a big minus sign in front, and you are getting dependency. I don't even care about the values. I'm getting the energy is proportional to the k square, kx squared. You can write this Okay, so for small k, this is equation of a circle. So you can write around the gamma, you can draw small circles. Yeah, I mean, you see how it's all tilted, so you cannot draw worse than everybody started. Yeah. A few of them, even small one, a few, as long as k's are small. Okay. Let's try to draw a big real zone that one can see more clearly. Okay. Not very symmetric now. Yes. It cannot be too much expected from this drawing on the blackboard. Now let's expand around the W point. So just a small amount. So W point is pi over A. You expand around there. For small case, small displacements come here. So it's just a cosine. I mean, it's a cosine pi over A minus x. We can write it step by step. You don't have to do the whole thing. Yeah, okay, fine. This can be done also, but she's doing in her head well, you can just add cosine of pi over A minus kx. Okay. For me it's much easier this way. Then I write the whole thing. It's cosine pi over A cosine kxa. And this kx is small here, no? It's minus or plus? Plus. You guys are fresh. Sine. It's not the repetition. Sine pi over a. Sine kxa. This is 0. And then you expand this for small kx, no? Kx is smaller arm, so now it's easy. This is -1. And then
So it's cos pi. Cos pi.
Yeah, without any.
yeah. So you will get this, and it's entering with a plus or minus sign. It's coming from here, minus cosine. So this will be 1 minus kx squared minus ky squared. Now you are centered at these edges. So, so you are centering a circle here, at this point, and drawing. So this is for the points close to the edge. Okay, this can be a bit wider. This can go up to some point. And then in between, what do we do in between? And this in between is non-trivial. This was kind of easy part. In between is non-trivial. So there is a mathematical way. We can find an expression when this remains constant, for which kx and ky relation. Or, which is maybe more physical approach, you start drawing energy along different directions. I would attempt this one, and then I can give you solution at the end of the mathematical approach. So you start drawing, and you start comparing at which point they have the same value, these three, let's say. So the energy along the gamma x, like along the gamma x direction. How to say energy along? This is not quite right. Can you draw? Gamma and x. And the gamma? This is for the gamma x, for the whole thing. Okay. Be careful. This is a trick, you know. Now you have here 2 minus cosine kx, which is fine, minus 1. Okay. So at the gamma, it is 0.
Gamma 0 and x is 2.
And 0 here is the E0 value.
Something. It should be.
It's 2 E0.
2 E0, yes. I think I had a more proper drawing at some point. Yeah, it should be more like a cosine, no? Not much better, but I mean, it has this, yeah, it's not, I wanted this form a bit, I didn't manage. Okay, a little bit better, yeah. Let's shoot this one on the top. Okay. Along gamma to W.
It should be the same.
No, only the same. Because here you have kx and ky, both pi over a. So you have the full thing you have to consider. And the gamma is the same, yes. But maybe underneath you can draw gamma to W. You can erase this part. So at 0 it is E0 again. I'm going to start from here. And pi over A, 2 plus 1 plus 1. So yeah, now it looks like the same width, but actually it's twice more. We used a different scale on this plot, the bottom plot. Yeah. So it's not the same. Here the energy is 4E0. Here it's 2E0. Here is 0. Here also 2E0. Along gamma x and gamma y is the same dispersion. So at this point 2E0, 4E0, 2E0. But along gamma to W, at which point it's equal to 2E0?
Pi over 2A.
Yeah, exactly in the middle.
Yes.
So here, this point, and this point, and this point have the same energy. In principle, we could prove it a bit more before we plot, but it has to be a line. So the iso energy line in the center, not too small, not too large, is just a line. And this you can also derive, and the shape in between is starting to vary a bit from the circle. It's something in between. So it's altered circle until it becomes a square. There was also a mathematical way to come to this, at which k you will have satisfied this. So if your kx is equal ky, I think minus pi over a. I think it was the thing. Yeah, it has to be this pi over a.
Yeah, the cosines cancel each other.
Yeah. And then, and this is the equation of this. So it can be obtained mathematically, but not everyone sees it right away, and this is a more physical way to arrive at the solution. Okay, so we determined the iso energy lines. The question was, if you have 1 electron per site in this crystal, draw the Fermi surface. It's not trivial like in the free electron system, but here we are lucky. Here, you can draw here. At least just give a sign. 1 electron, it's again half of the brilliant zone. And this has a particular shape, this feeling, that it's kind of easy. It's harder to say 35%. I wouldn't be able to say. 50% I can find easily. So which part of the brilliant zone? It starts going from here. No? It starts from here, and for 1 electron it will arrive. Yeah, because this is exactly half. This is a cute thing of this. This will be occupied. But you see, I'm getting a square here versus the circle in the free electron. Okay, and if you have 2 electrons, what will be the Fermi surface? This part I dislike in the problem. I think it's a bit, so it will keep filling. Now it will also have this shape. It will become a bit flatter. So it will keep filling, keep until only these parts are left. And then you fill the whole brilliant zone. Yeah, assuming only one band. And then if you fill it completely, is it a metal insulator?
Insulator.
But you have just one band. It's a, I don't like the question, so we can leave it aside. But important thing is to understand how the feeling occurs and to get a difference with respect to the electron. Thank you. Did you all understand the problem? It's not difficult, but arriving alone can be confusing. Okay, we are quite good actually. I would like to solve also the one I gave you, the first one I think in the other sheet. Not now because I want to try it. The relation system, the one which has this dispersion, a kx square plus alpha ky square. That's a very cute column. I would like to analyze it. It's useful, I think. And then if we have time, also number 2 in this sheet of this problem. And then it's one is much easier. The one with this, don't look at the solution. It's useless.
This first question is a little bit strange to me because the problem says that we are on 2D square lattice with
Okay,
lattice
let me just
spacing.
turn off the...
Okay.
It's here, no?
No, it's the spot.